Hello, I'm Mark Bowman. I work for the Tennessee Valley Authority Nuclear Power Division, and I'm going to talk to you today about the TVA ETAP Real-Time Online Monitoring Project. So TVA is currently underway with projects to install ETAP real-time systems at all of our nuclear plants. That's 3 stations and 7 units. You see here Watts Bar, Sequoia, and Browns Ferry nuclear plants. In my industry, a reliable source of electric power is critical to the safe shutdown of most nuclear power reactors. And that's why such a system as the ETAP real-time monitoring system will help us keep tabs on our critical safety systems. So what's the need for ETAP real-time? Well, the main benefits for a nuclear plant are state estimation, that is, getting data for the entire plant system just from limited sensors. Online monitoring, having real-time data and historical trending, event playback, the ability for troubleshooting and event investigation from the data that's stored, and predictive simulation or what-if analysis. Additional operational and historical knowledge of this type would represent major benefits to nuclear safety, operability, and operating costs. So if this is so great, why have we not done it already? What are the challenges for putting in an ETAP real-time system in a nuclear power plant? Well, most nuclear power plants already have a detailed ETAP design model, so it's not that. The real issue is that our plants were designed and built prior to the digital age and use mostly analog panel meters and indicators, things like voltmeters, amp meters, watt meters, breaker status lights, and so on. So we don't really have any built-in sensors to provide the real-time digital data that would feed an ETAP real-time system. And there are costs associated with getting this real-time data. There's design costs for sure, but there's also equipment qualification costs because in my industry, the equipment would have to be qualified to be installed. And then installation costs in my industry tend to be quite a bit more than in other industries. There's also risks associated with putting in the sensors that we need. For sure, there's installation risks, things like having unplanned outages. There could be impacts to the nuclear license requirements for safety system availability, and there could also be personnel safety issues, such as perhaps creating an arc flash likely situation when trying to install the equipment. There's also potential operational risks of introducing additional failure modes. Now let's talk about 3 aspects of building a case for installing an ETAP real-time system. The first aspect is the business case, and we always know we have to have a business case for everything we do. At my stations, one of my plants, for example, estimated that it's possible to eliminate some low margin issues on critical safety related systems and possibly eliminating a $1.1 million design change if we had something like this ETAP real-time data to compare to our design model. That's what we would call ETAP design model refinement. There's also event investigation and troubleshooting. So any kind of event in the plant, it could potentially save 2 to 3 shifts of investigation time to determine what caused the event. And there are some specific items that come to mind. We had a trip at Browns Ferry of Unit 3 in 2019. There was a diesel generator test failure in 2017. And multiple differential relay trips at our stations, 2016, 2015, 2012. We're estimating saving something like 16 to 24 hours of offline time per events like these, and they do happen periodically. So that's something like $800,000 to $1 million for each event. So that was the business case. What about a nuclear safety case? And I'm just going to take one event in the past few years. There was a tornado event near Browns Ferry nuclear plant, which caused a loss of off-site power. The plant itself was not damaged, but we lost connection to critical off-site power supplies that are important to nuclear safety. So the situation there was we had a serious nuclear plant emergency condition, no off-site power for about 5 days. And the bottom line is, without getting into too many of the details for this particular presentation, is the knowledge provided by an ETAP real-time online monitoring system could have allowed us to use offsite power about 3 days earlier, because it was actually capable all along, but without the transmission line SCADA system and without our normal ability to determine the adequacy of the grid, we didn't have any built-in plant engineering studies for the current plant conditions that we found ourselves in, because it was not a worst case. And this would have improved nuclear safety for the public had we known that we had offsite power available about 3 days earlier. There's also a nuclear operability case for having an ETAP RT system, and I'm going to use a case study, an event that happened at TVA at our Watts Bar nuclear plant. The nearby hydro plant had a fire in September of 2002. So the situation there was the nuclear plant was operating at 100% power, again, without an adequate offsite power supply, which is required to maintain what we call operability, which really just means we're operating in accordance with the station license. And we can do this for up to 24 hours, but we were estimating it would take 2 days to perform manual ETAP analysis using our design models to determine the adequacy of the remaining offsite power sources, again, using current plant conditions. We didn't have studies like that. So the knowledge provided by an ETAP real-time system could have supported continued system operability and saved us an avoidable shutdown. So we see there's a business case, there's a nuclear safety case, and there's an operability case, and those collectively build a pretty strong case for having an ETAP real-time system at a nuclear plant. Now let's look at the specific TVA ETAP RT system design concepts. First of all, our design scope is to obtain online monitoring data from the auxiliary power system, and it's the system we're after, not all the loads. We would have to put way too many sensors in to be able to gather data on every load in the plant, but just knowing how the system behaves is the goal. And we're going to focus on two things: offsite power circuits and Class 1E systems. And in my industry, those are the critical electrical systems that are important to nuclear safety. The primary users and stakeholders for this ETAP RT system will be design engineering, systems engineering, and our emergency response organization. Now, plant operators can use the benefits of this system indirectly, but the idea is the data would primarily go to systems or design engineering, and they would be a resource to discuss the implications of any event or any of the data with operations. These are our design objectives. First of all, the ETAP RT data should be available during all plant modes and plant events. Also, we want to minimize the number of new devices to be installed. That's very important. We talked about that earlier. In other words, let's estimate everything we possibly can from as little as we can possibly install. We want to have minimally intrusive installation. So basically that means let's utilize all the existing metering circuits that we can, sort of think about it as piggybacking over the existing meters, using things like auxiliary CTs to avoid breaking into a circuit, use our existing implant data network. We have Ethernet, fiber, and Wi-Fi running through the areas where we will be putting these sensors. Avoid required unit outages or board outages to the extent practical, and avoid personnel safety issues. So avoid having to do an installation where you would be putting workers in harm's way, for instance, being around high energy circuits or creating an arc flash event. Try to focus on installing these sensors in metering compartments and relay compartments where it's all low energy circuits. Also, very important is we partnered with ETAP for these ETAP RT systems and for the sensor design, because ETAP are the experts. They invented this technology, and we partnered with them to help us pick out appropriate sensors and look at what our specific installations are and what would be best there. We're also going to design using what we call stages for timely and efficient installation, and I'll talk a little bit more about that. This is an overall view of the Watts Bar nuclear plant auxiliary power system. And I know you can't read everything because it's zoomed out so far, but that's okay. The point I want to make is my critical electrical systems are down here. This is what we call the Class 1E system. This is my switchyard for the nuclear plant and a nearby switchyard of a hydro plant, and my offsite power actually comes from the hydro plant. The orange that you see here are existing data. So I do have some existing data points, voltage, current, and power coming from the hydro plant, offsite power circuit feeder, and I also have a summation of power data on these transformers. However, to get all the sensors I need in partnering with ETAP, we figured out we're going to need to put some smart meters, and that's what these red squares are here. So there will be one smart meter on each incoming circuit at our 6.9 kV shutdown board switchgear. And then we're also going to have what we call branch circuit monitors, and I'll show you a little bit more detail on that, but there's 8 of those. So there's one for each 480 volt switchgear. Here's 8 switchgears, and there'll be 8 branch circuit monitors. The status of the project is we obtained approval in 2020. We did a design study in 2021, and that was mostly when we were partnering with ETAP to figure out, where can we put these sensors, what type do we need, what's the best options. This year, 2022, we're doing the detailed design, and it's slated for installation in 2023. Likewise, here's a similar design concept for our Sequoia nuclear plant. This one will be about a year later. You can see similarly we have a few existing data points which are shown by these orange dots coming out of our switchyard, but we're going to plan to use the same type sensor design, putting smart meters at selected places on our medium voltage switchgear, and then we're going to put branch circuit monitors down on the 480 volt switchgear. The name of the game here really is, in order to do the state estimation, you kind of have to know what your inputs are. This is your input power, and I like to think of it as which way did it go. So you need enough sensors down the line to know, okay, how did the power split between here and here? How did the power split between here and here, and so forth. Now let's talk about the specific sensors that we'll be using. So for our medium voltage switchgear, the sensors that we selected, and they were tested and certified by ETAP for this application, are AccuVim L series smart meters. And these are typical smart meters. You can think of them that way, that you would use in a single circuit application. And in our case, we're using it for the incoming feeds. And like I said, we're going to piggyback over our existing metering circuits. These are a typical industry standard size. They're about 4-inch square. They can accommodate 4-wire, 3-wire, 2-wire, or even 1-wire systems for your PTs and CTs. They have a built-in Ethernet LAN module, which can supply Modbus TCP/IP protocol, which is compatible with the ETAP RT server, and they can be either panel or surface mounted. For our low voltage switchgear, the sensors that were selected, tested, and certified by ETAP were Anord Mardix circuit monitoring system sensors, which are also kind of known as a branch circuit monitor. I've got a little picture over here of, you may more typically think of a branch circuit monitor as being used in a power panel or a breaker box. And I thought this was a very unique and smart application on ETAP's part to suggest this, because what we have in our case on our 480 volt switchgear is one voltage measurement for the bus, but many currents in and out. And that's exactly what this branch circuit monitor is designed for. So its design is what you would need for having multiple circuits. We can get all the incoming and outgoing system feeds at this location. As I said, these were originally designed for circuit panels with 1 voltage input and up to 96 current inputs. Now we don't have 96, we only have about 9. But these also can accommodate 4-wire, 3-wire, 2-wire, 1-wire type hookup for PTs and CTs. They have a built-in Ethernet LAN module that can do the Modbus TCP/IP protocol, and these are meant for panel mounting. This shows the overall architecture of one of our ETAP real-time systems, and you can see we've got smart meters down below and branch circuit monitors down below. And the idea is that we would install a data concentrator somewhere near our 6.9 kV switchgear rooms, and another data concentrator somewhere near our 480 volt switchgear rooms. And these branch circuit monitors and smart meters would be connected via Ethernet to the data concentrator. And then we'll either go over fiber or Wi-Fi back to the ETAP real-time server, which is located near the plant control room. And what's really interesting about an ETAP RT system like this, and the real strength of it, people say, well, Mark, why wouldn't we just hook up smart meters, and why do we need ETAP real-time? Well, because we're getting about 32 points out of the 6.9 kV and about 88 points out of the 480. But by going up to the server, the ETAP real-time server, and using the state estimation, in other words, using our ETAP model, we can then realize about 15,000 points that are available for playback or real-time viewing out to the network clients. And also we save selected data to our TVA historian. So that's the real power, going from just a little over 100 points to 15,000 points. This slide shows the design of the ETAP RT server. It's going to be supplied and configured by ETAP. It will be one physical server containing two virtual servers, and that'll be the real-time server and the historian or archive server. And this just shows some of the specs that we chose for our specific application. As I said, we'll be installing this in stages. So we're putting stages together in our design packages. Stage one is what we're calling the infrastructure. And another way of thinking about that is everything that doesn't actually connect to operating plant equipment. So this stuff can be installed at any time without an outage, a unit outage, or a board outage. It can just be done during normal workweek scheduling. So that's all the ETAP RT hardware. We're going to locate the ETAP RT server and local console in our ERO Tech Support Center, which is near the main control room. As I said, we'll have a new ETAP RT server, and we're going to locate that in some existing TSC server racks. And we'll have a local console, the typical kind with like a slide-out keyboard, mouse, and screen. This also includes all new network devices and cables. So Ethernet from each new smart meter or branch monitor, and everything that needs to connect to the local data cabinets. We'll also have new local data cabinets, which will convert the Ethernet to either fiber or Wi-Fi, as I said, and then we'll have the some new fiber from the data cabinets to our in-plant business network. So these are the things that will get installed in stage one. So, we can put in the branch circuit monitors and the smart meters, we can put them in the compartments, but just not connect them yet to the PTs and CTs. We can install the Ethernet, the data concentrator cabinets, any fiber, we can install the server, we can install the workstation. So these things can be done, as I said, during any normal work week. And the idea there is it'll give the plant flexibility to install this without having to plan around operating plant equipment. Now let's talk about all the other stages, which are the sensors, actually connecting these sensors up to the plant equipment. At WattsBar, we'll have 24 stages. There's one stage for each device, and that gives the plant the flexibility if they're going to be in any of these metering compartments, like on the 6.9 kV shutdown boards or the 480 volt shutdown boards, they can choose to install these devices. And as they install each device, the infrastructure is already there. So once it's installed, it'll start communicating back to the ETAP server. And we anticipate over about a year's time, all of the stages will be put in just during normal work week scheduling. And so therefore, it'll take about a year to realize all the digital data coming into the server. We're doing that, as I said, in 2023 for WattsBar, 2024 for Sequoia, and we've yet to plan the Browns Ferry system, but we're going to start on that in 2023. Here's a detailed view of what the 6.9 kV shutdown board sensor connections will look like. We're using 3 phases of voltage to connect up to the metering PTs. We're only going to use 1 phase of current, and really the reason there is just it saves a lot of connections. And these smart meters are capable of calculating the 3-phase power from either 3, 2, or 1 wire connections. So we're going to use the 3-phase voltage so we can have the voltage balance measurements available to us, but we're only going to use one phase of current. To be as non-intrusive as possible, we'll be using isolation fuses for connecting the PTs. Therefore, we won't jeopardize any operating plant equipment. And we're going to use auxiliary CTs, which are a clip-on type CT. You can think of it as like a one-to-one CT, which is also very non-intrusive, very low mass. And we will use our existing switchgear DC power supply with isolation fuses to power the smart meters. And the smart meters will be mounted inside the metering compartment, so we don't have to like cut holes through the door or anything like that. Likewise, our 480 volt shutdown board stages, you can see the detail here for these branch circuit monitors. It's a very similar concept. We're going to use 3 phases of voltage, but only single phases of current. We're going to use existing metering circuits, isolation fuses, auxiliary CTs, all the same stuff we talked about before. One thing I'm very excited about is we've decided to build a simulator of our Watts bar auxiliary power system at a local university. That's the University of Tennessee at Chattanooga. And I've got some pictures here of the graduate students that are working on this project. But we actually built a simulator. And the idea behind the simulator is that we would simulate the entire power system as seen by the ETAP RT system. In other words, all metering connection points. So they're using an Opal RT simulator with our TVA auxiliary power system model inside it. And then we're going to output the digital output of each of those points back to the actual ETAP real-time server that we're going to be installing at Watts bar. And then for a couple of these signals, we're going to actually go from digital to analog. So in other words, we're using these double test sets to actually convert the digital to waveforms, analog waveforms. And the reason for doing that is we can thereby use our smart meter and branch circuit monitor actual equipment that will be installed in the plant. So this is a pretty close mock-up of what will be in the plant that we can operate. Think of it almost as operating in closed loop mode. Now, even though we haven't actually installed a system yet, by using the simulator, I can demonstrate what our system would look like. So here's a short simulation of an event, which is a loss of offsite power. You can see the diesel generators have started up. Soon you'll see their breakers close to connect them to the shutdown boards. There it goes. I've got the diesels connected on the buses that lost offsite power, and you'll see the diesel generators picking up load. Again, this is close to real. It's not exactly what you would see in the plant, but just enough to demonstrate the capability of the system and kind of give an idea of what the human-machine interface would look like. Well, thank you for your time and attention. That's the end of my presentation, and I hope this has been useful for perhaps your facility or industry if you're considering the installation of an ETAP real-time system. Thank you.